first. Okay, not the chicken and egg problem. Chicken first or egg first, that kind of problem. But whether it is moving charge come first, okay, then you get the force or the mechanical force come first when you get the moving charge. So it whether which one comes first. Alright. Then the next thing that we do, okay, is the Ampere's law. Okay, H dot dl, or you write properly, which is equal to H dot dl, which is equal to JDA. Wrong direction. Okay. H dot dl. Okay. H dot dl, or if they use V here, it is the same. Okay. V dot dl is equal to mu naught J dot dA, which is equal to mu naught I, because V is equal to mu naught H. Alright, so it's the same. Alright, so now we have Ampere's law, where it said that if you integrate over a closed contour, the magnetic field intensity or magnetic flux density, okay, what you get is the current enclosed. Okay, and the Ampere's law applies to all kind of contour. Okay, to apply to all kind of contour, it is applicable to all kind of contour. Alright. However, just like Gauss' law, okay, when Gauss' law applies to all sort of surface, all sort of surfaces, but we want to find symmetry, we want to find a good symmetrical surface where the integral for Gauss' law can be dropped quickly. Okay, same thing, we want to be able to find a contour, okay, which the Ampere's law can be dropped quickly. Now, Gauss' law, there are several scenarios. Okay, the surface can be many scenarios. The surface can be rectangular surface, can be cylindrical surface, can be spherical surface. Alright, but Ampere's law, it is more straightforward, because Ampere's law, the only symmetry that you have is when a current which is a long straight wire. Okay, so the contour is usually 2 pi r. So it's either 2 pi r head or 2 pi r b. Okay, which is only this. Okay, so in that sense, it is much more straightforward because it is only 2 pi r. There's no other contour which give you symmetry. Alright. Now, this part we said is key. Now, but what happens if we cannot find symmetry? That means we do not have a long straight wire. What are we going to do? Then we go to this Barksdale's law. V is equal to mu naught I over 4 pi ds prime cross u r double prime squared. Okay, then we have to go to the Barksdale's law. Okay, is when we do not have a long straight wire. We do not have symmetry. Then we go to Barksdale's law. And remember, ds prime is the elementary area, elementary length. Okay, in the directions of the current flow. Okay, ds prime is the elementary length in the directions of current flow. R double prime is the distance between the elementary current and the observation point. So this is R double prime. Okay, and UR double prime is the unit vector in this direction. Okay, so remember two things. One thing is ds prime is the elementary length in the directions of current flow. R double prime is the distance between this elementary current and the observation point, and UR double prime is the unit vector in in that particular directions. Okay, so now you have two laws now, one Ampere's law and one Barrett-Suffolk's law. Ampere's law is used when you have a long straight wire, Barrett-Suffolk's law is used when you do not have a long straight wire. Okay, so we've gone through a example. Okay, and we see that for that particular example, okay, when we have a ds prime along the z-axis, okay, and a ur over here, then the cross products of the two is automatically on this plane, okay, which is on the A5 dimensions. Okay, and this is usually true as well. Okay, but of course, if I turn it like this, it will still be true. That means the directions must be in that direction. Okay, because not always A5. Alright, it can turn to, if I turn it around, it can be A theta or can be any other value. Okay, but depending on how it turns the coordinate systems around. Okay, then that was the example for Barrett-Suffolk's law. This is examples for Ampere's law. Okay, remember, for Ampere's law, we always look for a circular contour. Okay, and circular contour, the integral always drops to 2 pi r times whatever, V or H. Okay, and then you find the total current involved. Okay, you find the total current. You find the total current. You either integrate the current density over the area, or you don't have to integrate. You know what it is already. You just use it. All right. Now we can also apply Ampere's law to a solenoid. Okay. Why? You say that Ampere's law is only for long straight wire, but solenoid is not a long straight wire. The reason why is because for long straight wire, okay, we know that the magnetic field is constant in a circular directions. But the solenoid, okay, solenoid, if we neglect the fringing effect at the two sides, okay, for long solenoid you neglect a fringing, the magnetic field is constant. Okay, and if the magnetic field is constant, we also can apply Ampere's law, because if we draw a contour like this, magnetic field outside is 0. The integral V dot dl is equal to 0, because although the magnetic field is not 0, but V dot dl is 0 because the dot product is 0. Same thing for here, and this one here just simply become VL. Okay. So Ampere's law can be applied also to solenoid, although it seems that there is no symmetry, but if we neglect the fringing, we are able to use Ampere's law as well. But for solenoid, be careful, remember, solenoid, there are so many turns, and each turns of the current must be counted. Okay, so we must turn of current counted. And when you deal with solenoid, also be careful. When you deal with coil or deal with solenoid, also be careful. Look at the questions, what is given there. You are given the number of turn or number of turn per unit length. Alright, so be careful. Alright, if number of turn per unit length, then at the end of it, you must make sure that you multiply by length. Or if you want to find the inductance, then the inductance is per unit length. Alright, so you got to watch out for the question whether it's number of turn or number of turn per unit length. Alright, so this is B. Okay, then we have the these boundary conditions. Okay, the boundary conditions. All right, we have Bn1 equal to Bn2. Okay, Bn1 equal to Bn2, and we have Ht1 equal to Ht2 if there's no current flowing through the junctions. Okay, however, if this is a conductor where there's a current flow, then Ht1 minus Ht2 must be equal to the current that's flowing. Alright? Because basically this is Ampere's law. So if we integrate around, if there's current, then it must be equal to current. Alright? Otherwise, it just Ht1 just equal to Ht2. This slide is a summary of all the boundary conditions that you have learned so far for electric field, for current, and for magnetic field. Alright, so these are this one is a summary of all the boundary conditions. And the next one we go to is Faraday's law. Okay, Faraday's law says that EMF is equal to minus d phi dt. okay, is the rate of change of flux. Alright, EMF is equal to minus the rate of change of flux linking whatever circuit that you have. Okay, but be careful, the flux linking, okay, the flux linking is equal to B dot dA. Okay, flux is equal to B dot dA. And either one of these can change with respect to time or both. If the flux, okay, if the flux density is time varying, is AC, not DC, then this one can change with respect to time. But if, just like this case, okay, this case although it's not AC, but it moves in and out, the flux is changing. Okay, but it can also be that the area is changing. Okay, the area is changing, very simple. How can the area be changing? Just like in this case here, the area is changing. Alright, or in the case of, let's say I have a long straight wire, I have this loop here. Okay, if I move this area, although this area seems to be constant, if I move it in and out, there is also a d5 dt. Because why? Because now this area is constant, but the flux density is changing with respect to time. When it is nearer, the flux density is stronger. When it is further, the flux density is weaker. Right? So if I move things like this, there is also, although it seems that this guy is a DC, nothing changing. This guy is area A, nothing changing. But when I move in and out, the flux density at this point here is changing. When nearer it is stronger, further is weaker. So there can be a lot of scenario, okay, where the flux can be changing. This one can be changing, this one can be changing, both can be changing, or seemingly both are constant, but actually they are changing because B changes by relativity. Alright, and the Lenz's law explains why there's negative sign here. The negative sign is that in nature, everything is trying to maintain whatever it is, just like what we call the is it momentum? Not momentum, what is the name? Inertia. Is it inertia? Inertia, I think that's right. Okay, so when something is moving, okay, it will keep moving until we apply a force to stop it. Same thing. Alright. So if a magnetic field, let's say, going through in the positive directions, going up, so okay, the magnetic field is going up, and if the magnetic field is going weaker, getting weaker, then the current that induced, or EMF that induced in this loop, okay, will be pointing in that direction. Because this one gets weaker, it will supplement, okay, the decrease. But on the other hand, if this one is get stronger, okay, get stronger going up, alright, then the EMF that induced will be in that direction, so that it will induce a magnetic field which opposing the increase. Okay, so that's what Lenz's law is about. Alright, and we look at coil. Okay, same thing. We look at coil. We say when we do coil, we can use Ampere's law because the magnetic flux is almost constant. Okay, almost constant, fringing neglected. Alright, and then we say that, well, in that case, we can find the so-called inductance. Okay, magnetic electric field, we have capacitance C equal to QV. And then we have resistance R equal to VI, but now we have inductance. Inductance equal to flux linkage divided by I. Okay, so either L or M is equal to flux over I. Now I write this way, but the flux, you have to be careful, the flux must include all terms. Okay, like for instance, Okay, the flux generated by this coil, let's say, okay, this coil, let's say there's a current flowing. Okay, the flux generated here must be equal to the flux generated by one coil multiplied by N1. Okay, the flux density. If the flux density generated by one coil is 5, then the total flux density must be N1 times 5. Okay, then the flux linkage link through here, because it linked through N2 number, so it must multiply by N2 again. So this flux here, must remember, must be the total flux. Okay, so this one I write L or M. L normally is reserved for self-inductance, M is reserved for mutual inductance. Alright, this is okay, same thing. Same thing. Okay, then finally we have done an example which is on self-inductance. Okay, self-inductance per unit length, because this is a long straight cylindrical cable. Okay, it's infinite cable. That means the inductance is infinity. Alright, and that's the reason why we need to have inductance per unit length. Okay, so that's about all that we have. Okay, so what we are going to do, we will do the tutorial. Okay, tutorial questions 1a. Determine the contour integral h dot ds where C is the closed loop in the horizontal plane as depicted in figure 1a with the 8 circles numbered 1, 2, 3, 4, 5, 6, 7, 8, denoting the positions of vertical wires carrying outward current I1, I2, I3, I4, I5, I8 respectively. Now the answer is pretty straightforward. Okay. If you really want to evaluate h dot ds, it's very difficult because you don't know the h, and then the s is so funny. Okay, how to integrate over? So you use Ampere's law, saying that h dot ds is equal to the current enclosed. So you must see, okay, your eye must be sharp. Which are the current that's inside the loop and which are the current that's outside the loop? 1, 3, 6, 8 inside the loops. Alright. 2, 4, 5, 7 are outside the loop. Okay, you got this one you gotta have a very sharp eye, alright? Take a look closely. Okay, see whether you can see that 1, 3, 6, 8 are inside the loop, C, inside the closed loop C, and 2, 3, 5, 7, sorry, 2, 4, 5, 7 are outside. Alright? Okay, this one really testing the eyesight. 2, 4, 5, 7 are outside. Okay. But this one got nothing much to explain. Alright. Now the questions 1b, an electron is initially traveling with velocity v equal to v1 ux plus v2 uz, where v1 and v2 are constant. Explain what you expect to observe after it enters a region with uniform magnetic field B equal to B naught uz, where B naught is constant. Alright, we have velocity V equal to V1 ux plus V2 uz, and V is equal to V naught uz. Alright, this is what you have. You have V here, you have V here. Now you look at these equations here. This cross this. This cross this. So the electron coming in. Okay, the electrons coming in. Okay, electron coming into the magnetic field. Electron coming into the magnetic field, and these equations will hold. Okay, when it comes to these equations hold, you can see that velocity cross magnetic field. Straight away we say that this component of velocity will not play any part because uz cross uz is equal to 0. Okay, the two velocities are the same, so it's not, there is nothing okay. Now, then the next thing is that, okay, what happened to this component? These components of the velocity. This component of velocity. V is V here. Okay, V is V here. Sorry, yeah. Have I drawn wrongly? Have I drawn wrongly? What is the? Yeah, you drawn positive. Okay lah. That means this one. Okay, that means my axis is drawn wrongly. All right, doesn't matter. I said drawn wrongly because the question say electron, okay, it's moving in the positive ux directions, okay, but the solution draw this one as positive charge, and of course electron move left, positive charge move right. Okay, so if the electrons move here, so the x-axis should be up and not down. Okay, so I've drawn this one wrongly. I think I will just change it. Okay. Okay. So electron is moving in the positive x directions. Okay, electron is moving in the positive x direction, but the positive charge then moving in the negative x directions. Okay, electron then this one positive charge is moving in the negative x direction. Then you have the B cross F. Okay, B, where's Z? B cross Z. B is going down. Okay, Z is going in. Okay, the force is this way. Okay, B going this way. This is the positive charge. Positive charge because F is equal to QU cross B. That is a positive charge. So electrons moving this way, positive charge moving this way. B U cross B is equal to force. Okay, U cross B equal to force. So you can see that the force is actually perpendicular to the directions of travel. The force is perpendicular to the direction of travel, and this is become a centripetal force. Okay, so this is a centripetal force, and then the charge will be actually spinning around. Then the charge will be spinning around. Alright, the charge will be spinning around. But then, okay, in the sense that, alright, when the charge will be spinning around, and which also experiencing upward motions. Now, somebody tell I don't get confused, huh? Okay, we get confused, huh? There is also another component of velocity over there. Okay, there is also another component of vertical velocity initially there. All right. Then what is the, this part is mechanical, okay, this part is mechanical. mv squared r is equal to force. Okay, force is equal to mv squared r. Force is equal to mv squared r. That is your centripetal motions. Okay, I don't like this because I forgot. This one I learned in high school. I forgotten what it is already. I just use the formula. Okay, okay. F is equal to mv squared r, where F is equal to qv1 v naught. Okay, which is from here. Okay, it is from here, and from there you can find the radius of the circular motions. All right, as I said, this is mechanics. All right, any questions? Any questions?
So what does the y-axis actually stand for?
Sorry?
What does the y-axis actually
Y-axis.
Yeah.
No, you see, when this one move like this, so when you move until here, okay, move until here, you can see that the force will be the central, so it just go around. Okay, it just go around because when this is mechanics, right? When you have a velocity, when somebody moving in like this direction, you put a force in that perpendicular to it, so you follow a circular path. Okay, so and the force must be always perpendicular to it. You see, if it's like this, the force is perpendicular to it. So the force must be always perpendicular to it in order to get a circular motions. This is mechanics. This is not electromagnetic. You remember the mechanics in high school or not? That's the part that I remember. Am I correct?
So the charge is going up.
Sorry?
The charge is going up.
The charge is going up. Let me see. Actually, it might not be the charge going up. This one might be a typo there because the electron is going up. Electron is going up. So the charge is not going up. The charge will be going down. Now, I hope that this thing don't fly away. So this is what it is all about, right? Correct or not? When you have a circular motions, you must have a force that is always acting towards the center. This one there could be a typo in the solution. Let me check in the. Okay. Okay, questions 1C is a bit more difficult. Okay, questions 1C depicts a current carrying wire formed by circular segment at radial length. Derive an expression for the magnetic flux density factor and P, which is the common center of the circular segment. Alright, what it means is that there is a wire segment this way, formed this way, and the current flow in this direction. You are asked to find the magnetic flux density at the point P. Okay, flux density at the point P. Okay, what is this one here? Now, alright, this is not a long straight wire problem, so it's a Biot-Savart's law problem. Okay, Biot-Savart's law gives me this. Okay, Biot-Savart's law gives me this. And remember, the important thing is ds double prime, ur double ds prime, r double prime, ur double prime. Okay, so you try to identify all these things for all the wire segments. Now, for segment 0 to 1, for segment 01, segment 0 to 1, what is my ds double prime? My ds double prime equal to minus dx ux, right? Segment 01, current going this way. It is in x directions, so ds double prime equal to minus dx ax. Okay, now let me draw it. Okay, I take this segment here. Okay, so this segment is equal to minus dx ux. Okay, now if this is the point P, this is my r double prime. My r double prime is equal to x. Because from here to here, if this is x-axis, it is equal to x. My ur double prime is just equal to ux. So my ds prime cross ur double prime give me 0. Because this one cross this one is 0. Parallel wire. Now, then what happens to segment 0, 1, 2, 3, 4, 5? Now, segment 4, 5, segment 4, 5, us prime is equal to dx ax. Right? If this is like this here, this element is dx ux. R double prime is x. This is I beg your pardon, this is minus ux, okay? Because this distance is r, when you're pointing inwards is minus ax, minus ux. So this one is also equal minus ux. The cross product is still equal to 0. Why is not ux, is minus ux? Why is it minus ux? Because it is pointing from here towards P. Alright, pointing from here towards P. Now, then for the segment 2, 3, for segment 2, 3, this thing here, this is what? This is equal to d rho or dr minus d rho u rho. Or they use r here, is it? Doesn't matter. Use r also can. Minus dr ur. Okay, so this is minus dr ur. Then from here to here, this is r double prime. So r double prime becomes r. And what is ur double prime? Is minus ur. Because this is pointing downward. Okay, and the cross product is also 0. So you can see that although the wire looks so strange, 0, 1 has no contributions to the magnetic field here. 2, 3 has no contribution to the magnetic field here. And 4, 5 has no contributions to the magnetic field as well. So out of the 5 segments, 1, 2, 3, 4, 5, 3 segments are already gone. Okay, so we left with only segment 1, 2 and segment 2, 3 with contributions. Okay? Now we are going to do segment 1, 2 and segment 2, 3. Okay, segment 1, 2. Segment 1, 2. Segment 1, 2 is here. Cylindrical coordinate system. This is equal to R d5 A5 or U5. Okay, which is very simple. R double prime, which is equal to the outside is A or inside is A. Outside is A, right? Okay. Or B. Outside is B. Okay. R double prime is equal to B. Is a constant. Okay. R double prime is equal to B is a constant. Now, what is U R double prime? U R double prime is equal to minus U R. Okay, U R double prime is just equal to minus U R. So this one cross, what do you get? This is also, this R d5, this is a constant, so become a B. Okay, so I have this one become, this cross this, I have a B d5 and U5 cross UR. What do I get? U5 cross UR, what do I get? UZ. U5 cross UR. Okay, U5 cross UR. U5 cross UR minus UZ. Okay, but because of this minus, so we have plus UZ. Okay, U5 cross UR is equal to minus UZ. Okay, U5 cross UR is equal to minus UZ. But because of the minus there, so minus minus plus. Alright. So with that, we can do the integrations very easily. Okay, so now it becomes B d5 UZ. They use theta prime there. Okay, B d5 UZ. Okay, so now B d5 UZ and R squared, R double prime squared become B squared because R double prime is equal to B. Okay, so this one, do it. Integration from 0 to 2. Okay, that is segment 2, 3. Alright, how about segment 3, 4? Segment 1, 2. Segment 3, 4. Segment 3, 4 is here. Segment 3, 4 is here. Now, segment 3, 4 is here. What is your ds prime? ds prime is A d5 minus U5. Minus because it is pointing in that direction. Okay. Now, then what is the R double prime? R double prime is just equal to A. U R double prime, same thing, is equal to minus UR. Alright. So when you cross this one, negative, negative, positive, this one becomes A d5 UZ. Okay, so this one becomes minus a d5 uz, and r double prime squared become a squared. Okay, so integrate from 0 to theta, you get the solutions. Okay, so when you do Barrett-Savage's law, remember no matter what kind of segment they have, remember to break it down to straight segment. Straight segment or curved segment, one segment by one segment. Okay, don't try to do all at once. Do all at once is very confusing. Cut it down to one segment by one segment by one segment. So you do it slowly. Okay? Any questions? Any questions? Any questions? Okay, now we look at the next tutorial questions. Okay, figure 2 depicts a rectangular wire loops of length L and width W, which is placed in the vicinity of long straight wire. Determine the mutual inductance between these two with separation S. Okay, remember with separation S. Okay, so if the S is different, the mutual inductance is also different, as you can see that. And the answer here, S play a part. Okay, L play a part, W play a part, S also play a part. Alright, so mutual inductance depending a lot on the spacing as well. Now, okay, to find the mutual inductance, always assume a current on one of the circuit and then find the flux linkage to the second circuit. Okay, this is always done. Always do it that way. Now, in this case, we assume a current on this one and find the flux linking here. As we have mentioned in the lecture, this is obvious because if you assume a current here, the flux density is just simply Ampere's law. Very simple. But if we assume a current here, the flux density got to be done by Barrett-Savage's law 4 times, which is crazy like hell. Okay, and then of course you have to integrate over an infinite area. Double whammy. That's what they so called. Alright. So if we assume that Ampere's law, assume a current in a long straight wire, then the Ampere's law V5 is just equal to mu naught I over 2 pi r. Okay, mu naught I 2 pi r. Then the next thing that we want to find the flux linkage. Flux linkage is equal to B dot dA. Okay, so in this case here is B dot. Of course, if you want to write it in terms of elementary area, it is just dx, dy, because it's in our xy plane, uz. Alright, dx, dy, uz. If you write it, you want to write it in the proper manner. But what is this B? Okay, my B is given here. B is equal to mu naught I over 2 pi r u5. That sounds a bit troublesome. Okay, a bit troublesome. Then how am I going to write this one become this? Okay, because it's supposed to be B dot I. Well, B is B5. Okay, B is B5. But when it's on the XY plane, okay, if this is my X, this is my Y. Okay, this is X, this is my Y. B5 is now what? U5 is now what? R become X now. R become X now. 2 pi X minus uz dot dx dy uz. Okay. Now, but why is it different from here? But why is it different from here? Why is it different from here? Now, the difference from here is that, okay, this and this gone, equal to minus mu naught I 2 pi x dx dy. What is the difference between this one and this one? This one is, if you look at it, the flux density is constant with respect to y. Flux density is constant with respect to y. Alright, constant with respect to y. Therefore, you can write it in terms of mu naught I 2 pi x dx integral of dy. And this is become L mu naught I 2 pi x dx. You can see that now it becomes like this. Mu naught I L 2 pi x dx. Now, so that give you one hint is that be observant. Okay, be observant. Look at the questions. In this case here, I just write down elementary area dx dy uz. But if I observe that, okay, due to Ampere's law, the magnetic flux density is not changing in that direction. I can always write the elementary area instead of dx dy uz. I write the elementary area like this. So the elementary is L dr or L dx. You can see that the elementary area is L dx. Okay, so I can write the elementary area this way because basically I recognize that the flux density is not a function in that direction. Okay, it's not a function in that direction. Now, there is also a problem is that there is a minus sign here, there is a minus sign here, there is a minus sign here, and this minus sign, if you perceive here, okay, there is no minus sign here. If you perceive here, the flux have a minus sign. Okay, the flux will have a minus sign. But does it matter? Does it matter? Because for inductance is equal to the flux per current. Okay, whether flux linking these directions is flux. Flux linking that direction is also flux. So there is no issue. So at the end, we can just ignore this minus sign. Okay, and we can just ignore the sign here actually straight away. Not straight away. And if we do it this way, okay, so now my mu is here, mu naught I over 2 pi r. This small little elementary area is L dr. This is dr, L dr. Okay, so the total flux is just integrating from I equal to S plus W. Okay, and that's what you get. And the mutual inductance M equal to 5 over I. Okay, this one I just want to preempt some of your questions. Okay, what happens if there's why there's a minus sign here? Why I can write this way? Okay, you can draw the elementary area this way because basically we always started from here. Okay, but we know that okay it is a constant with respect to y direction, and if it's constant with respect it's constant with respect to the y direction, then when you integrate, okay, this one will come out as L anyway. So this one you don't even really have to write it in terms of elementary area. You can write the area this way. And if you want to follow, okay, correctly, then you find that there's an I like this, then the flux going that way, then the flux become negative. How? Well, does not really matter because you can also assume a current this way, so the flux will be in the correct direction. Alright, so basically inductance is still, mutual inductance is still equal to flux divided by current. Okay? Any questions? Any questions? Sometimes you don't just look at me, alright? If you have problem, you let me know, okay? Or else I will just assume that you do know. Okay, don't just look at me. Yes. Okay. Figure 3 depicts a triangular wire loop OPQ carrying a current I in that direction. Derive expression for the following. If the uniform magnetic field in the vicinity of the loop is given by B equal to B naught Uy, where B naught is a constant, magnetic force exerted on the 3 arms of the wire loop, magnetic torque exerted on the wire loop when pivoted about PQ. Pivoted, that means that PQ is always stationary, alright, which is fixed. Comment on the results that you obtain. I will mount this one on the IBLE as well, alright? Okay, once again, when there is something, not a long straight wire, you have to work segment by segment. Okay, segment by segment. Don't try to do everything all at once. Alright, so we have force is equal to IDS cross B. Okay, this is what we have. Force equal to IDS cross B. So we look at the 3 segment. Okay, no force on OQ because DS is in that directions. B is also in that direction. DS and B are parallel. So force is equal to 0 because DS cross B is equal to 0. Now, on arm PO, ds equal to minus ds ux. Okay, ds equal to minus us dx. B is equal to duy. B is equal to duy. Then F is equal to I minus ds ux cross buy. Now this ds along here is also dx, right? So dx. So this one dx, this one become, integral of 0 to ai x cross y into z b uz dx, which is equal to there's a minus there, sorry. Okay, which is equal to minus BIA to Z. Alright? That one is quite okay. Now, on RQP, now you can do it this way or you can do it this way. There are 2 ways of doing it. One way is you want to maintain this one. You want to maintain this ds. Okay. So along QP, ds equal to, you resolve into 2 components. Okay, because it's going downwards. Okay. ds cosine theta. This is ds. ds cosine theta is ux. Okay, I draw it down. this is a vector. This is ds cosine theta ux, if this angle is theta. This is ds sine theta uy minus. This is ds cosine theta ux. This is minus ds sine theta uy. So minus ds sine theta uy plus ds cosine theta ux, and then b equal to buy. Then you take the cross product. Take the cross product, it is equal to b cosine theta ds uz. So you put down in the integration, finally get bia. Now, but actually, you don't have to be so troublesome. Okay, you don't have to be so troublesome, because remember, we can also do it using our general terms. General terms, ds is equal to dx ax minus dy ay. Because in a general, it's always remember, an elementary area, an elementary distance in the x direction is dx ax, and elementary length in the y direction is dy ay. But this guy is just pointing downward, so it's just like this. Okay, so if you write this, then ds cross b immediately give you b dx ux, and then you integrate. That's it. Okay, you don't have to do it so in such a messy way. All right, so you can actually do it in the general terms. Now, then the answer is that, okay, this one got no force. This force is minus bia uz. This force is bia uz. So the net force is equal to 0. All right. So the net force on the loop is equal to 0. Now, magnetic field is more difficult as compared to electric field because of all the cross product. Okay, all the cross product, the vectors start to change directions. Okay, so be careful about this one. Now, then finally, what is a torque? When this QP is fixed. Now, this QP is fixed. So how does it look like? It's like this. This one is fixed. This one is fixed. Okay, so this guy is fixed down here. This guy is fixed. So this one has no force. Just now we already determined that this one has no force. This one has force. So this guy is fixed. This one has no force. That means this force will be just pushing it this way. Just now is because this guy is pushing this way, this guy is pushing that way, so the net force is equal to 0, right? So now this one is fixed, so this one no force, this one fixed, this one become pivoted, so it becomes like this. Okay, so that's the torque. Now, to do the torque, you can do it by using the first principle or using the result is already known. Okay, we see that the force acting on the arm OP is uniform. Why? Because you see, dF is equal to I ds dx cross b u y. This ds is dx. Okay, these are constant, this is constant, everything is constant. So on here, if you take a small little ds here, it has the same force as a small ds here. So it's a constant. So if the force is constant. And if the force is constant, we can take the total force multiplied by the perpendicular distance. This is the torque. What is the torque is all about? This is perpendicular distance. Must be perpendicular to the pivot. Okay, not perpendicular to the force. Okay, the force is this way. So this distance is this. Alright. So now torque equals F times distance, and this distance is A by 2 sine theta. Okay, so this is the dot. This is again mechanical. Okay, this is again mechanical. Or if I do it from the first figure, d dot, the small dot, is equal to small force times distance. Okay, small dot equal to small force times distance. So the small dot is going to be I dx times A minus x sine theta. Now this one, can you see why this distance is A minus x sine theta? This is A, this is x, this is A minus x. Okay, this angle is theta, this is A minus x sine theta. Alright, trigonometry. Okay? This is 90 degrees, this is A minus x, this is theta, this is A minus x sine theta. Alright, this is trigonometry. Alright, so once you get that, you integrate again and then you get the final results. Alright, so these two questions is a bit more weird because it involves mechanical things also. Any questions? You have problem, please ask. All right, don't keep it until on the next 7th Thursday. Then I get a lot of emails.
So next week or email.
Sorry, this week I got.
Next week.
Next week.
Yeah, next week.
No, you better raise your hand now. Which one you don't understand?
So you don't know what you don't know. That's the problem. So you must go back, then you revise, then you know what you don't know.
You must at least go through your tutorial before you come.
So I tried lah. Not easy.
I know, but at least I post the solutions ahead of time, right?
Cross reference also gets fine.
Yeah. You see, the best #1 student will be able to don't look at the solutions, work out the solution by himself or
But I'm not
herself.
#1, sir.
Okay, #1. Then #2 is that with the help of the solutions, he or she can work out.
Neither am I there.
Then minus the #3 is cannot work out the solution, but look at the solution, understand.
So not there.
But you haven't looked. Then you don't count. You should look first. Okay. Then #4 is that you look at the solutions and you don't understand. #5 is maybe you are #5. You don't look at the solution before you come. No, okay, at least look at the solution before. No, at least when I explain, you understand what I'm explaining, you see.
I understand a bit.
Understand a bit, okay lah.
Everything a bit, you learn something.
Okay lah. This is the final tutorial solution of the questions already. Figure 4a, 4a 4b don't have lah. Figure 4a depicts a circular wire loop with radius r equal to 50 cm, which is connected to a resistor with resistance I equal to 100 ohm. Uniform magnetic field B in the vicinity varies with time in accordance with the plot given in figure 4b. Sketch the variations of the current flowing as a function of time. B is in the plus z directions as denoted by the circles, and the corresponding positive convention for the circular loop is given by the arrow. Okay, obviously this is Faraday's law, alright? Faraday's law, EMF equal to minus d phi dt is equal to minus d integral of B dot dA. Okay, since A is constant with respect to time, okay, and B is constant with respect to x and y, alright, so we do our integration first, okay, because remember the integrations, B dot dA, the integration with respect to x and y and the differentiation with respect to time. Okay, so they can do separately. All right. So if there is no change in A with respect to time, there's no change in B with respect to time. So B dot dA simply give me dz pi r squared. Okay, because B is a constant. B is a constant with respect to xy coordinate, and the loop is on the xy plane, which is area equal to pi r squared. So this area equal to pi r squared is just B, is just bz pi r squared. Alright, this is just bz pi r squared. Okay, so it does multiply out. Sorry, now it's equal to minus pi r squared dB z dt. Okay, so the EMF is equal to minus pi r squared over resistance. Oh, sorry, this is the current. Okay, current is equal to EMF over resistance equal to minus pi r squared over resistance dB dt. Alright, dB dt. So we can write down a general formula for the EMF induced in the loop and also the current flowing in the loop. EMF induced in the loop is given by the Faraday's law equal to minus d phi dt, and since phi is equal to B dot dA, and since B and A are constant with respect to xy plane, is just given equal to B pi r squared. So it becomes minus d this thing dt. Okay, this is the EMF. Then Ohm's law, current is equal to EMF divided by resistance. Okay, Ohm current equal to EMF divided by resistance. So this is the general formula for the current flowing. Alright? So now we look at B now. Okay, B is not constant with respect to time. Okay, it is constant with respect to xy plane, but it's not constant with respect to time. So when B is increasing from 0 to 5, when B is increasing from 0 to 5 in 2 seconds, so dB dt equal to 5 by 2. Alright, B increased from 0 to 5 in 2 seconds, dB dt equal to 5 divided by 2. If that's the case, you substitute dB dt equal to 5 by 2 in here. Okay, you get minus 19.6 milliampere. Okay, because it defines anti-clockwise positive, so minus is clockwise. Minus is clockwise. Okay. Now, when for the time t equal to 2 to 4, time t equals to 2 to 4, B is a constant. B is a constant, dB dt is equal to 0. If it's 0, then when you sub in here, the current is also equal to 0. Alright? So you can see that for first 2 seconds, the current is down here minus 19.6 milliampere. Next 2 seconds, the current is equal to 0. Then the next 2 seconds, from here to here, next 4 seconds, from 4 to 8, B drops from 5 to 0. So B dropped from 5 to 0 in 4 seconds. Alright, so dB dt equal to minus 5 over 4. dB dt equal to minus 5 over 4. If that's the case, you sub here minus 5 over 4 into these equations here, you get the current I, which is equal to 9.8 milliampere, and it is anti-clockwise directions. Okay. Finally, for time greater than 8, dB dt is again equal to 0 and current equal to 0. So if you ask to plot, this is how it looks like, the current plot. Okay, this is very simple. Alright, any questions? Sorry?
Okay, we'll post all the solution in here. It's fun doing those in IBM here.
Yes. I'll post it on the Yeah, I'll post it on I'll put it on IBLE after when I get back. directions. Now, okay, as I mentioned earlier, alright, magnetic field is the most difficult part because it involves cross product. Okay, magnetic field involves cross product, it is the most difficult part. Alright, it is more difficult than electric field. Of course, we don't count all the divergence theorem and Stokes theorems lah. Okay, we don't count the divergence theorem and Stokes theorem. Divergence theorem and Stokes theorem basically is to prepare you, future ready, right? Future ready. So
future ready.
Future ready. You want
how many weeks later in the future?
Yeah, future ready lah. No, future ready. So we prepare you for the future. That's all. I mean, if you next time you don't even know there's such a thing as Stokes theorem, then how can you go further study, right?
That's true.
Yeah. Okay. Now, but this will be the magnetic field is the most difficult one. Electric field is the next. After that, your plane wave and then transmission line. So as I said, so from after the midterm breaks, everything is going not downhill, but the difficulty is going downhill. All right, so don't have to worry. And you see, my last year's class. Okay, I don't know it's because due to their hard work or what. So the first CA1, we have 4 classes, right? First CA1, they rank 4th.
Oh,
but when it comes to CA2, they rank 2nd. So I don't know if because of their hard work or because I told them really, not to worry.
So pressure is on. Pressure is on.
No, it's not. Okay. Another simple class test, and that's it. As the last class test, everybody got 100 marks. So this one, I expect everybody got 100 marks. So. Either the current is flowing from A to B2 or D to R2, okay, or both this way or both that way, or both that way or right there. The first one is A to B2 this way. The second one is D to R2 this way. Right? A to B2 this way, D to R2 this way. Both A and B, or A and D, either A or D. Yeah, that's the spinning. Okay, this is directions of the spinning coil. This is the direction of the spinning coil. Yeah, the coil spinning. Oh, you got better. This one is a pointer. This one.
current.
D 是那个 C 在那边这里 P 在它的那个 back side，因为它的那个它经过那个水流管路直接进去，然后这边。
I think E is positive. So it's going all this way, right? Current going from A, B, C, D. Current EE11 If this is your B, right, it's turn, right? So now this one is because it's turning down, right?
This right, the force is going down. Force is going down.
No, the other way. You cannot like that, because this is bro, you don't look at it. This is the force, sorry, this is the force. You like that, force is going down, but you go it up,
Okay. Now one more time, A means both current flow from A to B in that direction. Okay. A means current flow from A to B2 direction. Okay. B means current flow from D to R2 directions. Okay. C means that the current flow in both directions. Okay. And D means there's no current at all. Okay. And somebody just asked me, is the circuit closed or not? Yes, I'm not tricking you. I'm not playing trick on you, alright? It's not wrong, okay? Just now somebody asked me.
So the
current, let's say the current B to R2. The current is going, the force going downwards, right? So it means your field is going this way, the current is going this way. Then if it's the other way around, right? If it's the other way around, right? It means the current is going this way, the force is going downwards. Your field is going this way.
not the south one. So north south like there, right? So this one has to point inwards. So this one goes down, then the current is going this direction. Then after that, when you go the other side, right, the force is going down. Then the inside there, force is going up. Right, so north and south side there. So yeah, correct. So yeah, the current is still going. Current is still going. So it's like that, then like that. Just like that. So like current Like when you draw CD 的 portion 是 north to south 吗 ？Force 是 upward， 这样。
这是 B 耶。
我只能confirm不是 DU 对呀。
他的出现这样，这超了一滚的这样子。
有分别没？
current at that moment. Okay, don't go and consider the current time here. Look at that moment.
At that moment 啊，不要想很多。
At that moment, it's AC, so we go the other way. But then you say at the moment, this moment that is going this way.